Good morning. My name is Ian Gould. I'm the current director of the School of Molecular Sciences here at ASU, and today I'm totally delighted to welcome you as the newest Sun Devils, and more importantly, as members of the School of Molecular Sciences. Molecular Sciences is all about chemistry and biochemistry, and chemistry and biochemistry is all about basically everything. I mean, everything you hear, me and you and the table, the glassware, everything is about chemistry and biochemistry. Chemistry and biochemistry is all about molecules, molecular science, atoms and molecules we can't see, and yet we know lots about them, right? We can control them, we know what they do, we can use them to our benefit, for society's benefit. And how do we do all that if you can't see them? So those are things you're going to be learning about as you work through your classes here and your courses. But I don't want to do that today. I want to do something different today. There's lots of time for learning later. Learning's hard work, and we're not going to work hard today at all. We're going to talk about the aspects of chemistry and biochemistry that many of us as chemists, what brought us in here in the first place. And that is, although we can't see the atoms and molecules, we can often see matter changing as a result of the atoms and molecules changing. And by making observations with your eyes, you can get some information about what the atoms and molecules are actually doing. And that's changing matter, and changing matter we believe is kind of fun. It can even be entertaining in addition to education, and let's focus on the entertaining part today. There's plenty of time for learning and education later. So we're going to show you some entertaining changes which are happening to atoms and molecules. You're going to see them, so you're going to know when the atoms and molecules change. And we sort of pick the things today which are more fun, right? Because that's what we want to do on your first day here at ASU. So I'm going to show you something. Several of my colleagues are going to show you something. Let's do some chemistry. So let's do a chemical reaction. And you watch very carefully and see if you can see something happening. Then you know you got a chemical reaction. So to do this, I'm going to put on my safety glasses. I'm super safe. Let's go. And remember, watch carefully. Did you see it? No, nothing happened. It was boring, wasn't it? All right, let's see if we can actually make something happen this time. Let's add some more. And again, watch very carefully, okay? All right, more like it. Look, we have a rainbow. Cool, huh? Watch carefully again. All right, watch carefully. There we go. But we're not done yet. Pretty cool, huh? Obviously, you saw the colors change. Cool color changes, we get all that. What was really going on? What we were doing there was reactions between acids and bases. Everybody knows that an acid reacts with a base, right? But why? I mean, why does an acid react with a base? It's one of the most fundamental things in all of chemistry. Acids react with bases. Are you telling me that nobody told you why an acid reacts with a base? we're going to tell you why acids react with bases. Okay, so we just did some cool chemical reactions, acid-base reactions in water. Water's not the only important state of matter, right? It's more than just liquids. So Jim Klimaszewski is now going to show us some really cool stuff connected to gases and how gases work and what are the laws controlling the physical properties of gases.
Hey class! Welcome to ASU School of Molecular Sciences. Today we're going to do some demonstrations regarding the gas laws. To begin with, I will start with Boyle's law, the inverse relationship between the pressure and the volume of a gas. So I can demonstrate that with this piston between two blocks of wood. When I put pressure onto the top block, the piston goes down and the volume inside decreases. So as pressure increases, volume decreases. Well, so what? What can you do with that? Well, I'm sure you've already done some things with that. Here I happen to have a Boyle's law apparatus. It operates on the same principle. When I apply pressure, the volume inside this chamber decreases, and then the extra air goes out to inflate your tires. So that's one application of Boyle's law. Another one you're experiencing right now. Every time you breathe, you are experiencing Boyle's law. So think about it. When you inhale, your diaphragm drops down, your rib cage rotates upward and outward, and that increases the volume of the thoracic cavity. The increased volume results in a decreased pressure inside your thoracic cavity. That allows the higher air pressure to push in and inflate your lungs. So that's inhaling. When you exhale, the opposite happens. Your diaphragm pushes upward, your ribs rotate downward and inward, decreasing the volume, increasing the pressure, and you exhale. So every time you breathe, that's Boyle's law. All right, so we'll move from Boyle's law to another law that looks at the direct relationship between the temperature and the pressure of a gas. To illustrate that, I happen to have some liquid nitrogen. You can see it's boiling away right now. Its boiling temperature is about negative 300 degrees. Right. While that's settling down, I will show you this apparatus. It has a fixed volume. The sphere is solid, everything is rigid here. Okay, this is hollow, so this is filled with gas. And the amount of gas does not change, the volume does not change. So when we change the temperature, it will allow us to see the effect on the pressure by the needle moving on the gauge. Okay. So let me put this into the liquid nitrogen. And if you watch the gauge is going down. That demonstrates the direct relationship between the temperature and the pressure of a gas. So why is it going down? Well, those gas molecules are getting colder, they have less kinetic energy, they're moving more slowly. So they're colliding with the walls of the container less frequently and with less force. And that reduces the pressure. Now, we can do the opposite here and increase the temperature. And as we increase the temperature, we're applying heat. Those gas molecules inside are moving faster, colliding with the container walls with more force and more frequently, and that increases the pressure. So there we go. So sometimes that is referred to as the Gay-Lussac law, sometimes it's referred to as Amenton's law. Either way, it's still the direct relationship between the temperature and the pressure of a gas. All right, finally we'll turn to Charles' law, and we'll look at the relationship between the temperature and the volume of a gas. So here we have a special elastic container the volume will change. Now the pressure will not change. This is an open container and we're under 1 atmosphere of pressure, so that remains constant. The amount of gas, the number of moles of gas, does not change. The balloon is sealed. So when we put it into the liquid nitrogen, and this balloon, by the way, is filled with hydrogen gas, which is why it was floating. So I'll set it in here. Now it's cooling off, and again, those gas molecules are colliding with less force and less frequency, but the pressure is equalized because it's staying under 1 atmosphere of pressure, so that's not changing. So the volume of the balloon decreases. Now, hydrogen balloons, as you saw, float unless they're really cold and more dense than air. Then as the temperature increases, the density decreases, and the balloon floats again. So there we have some gas laws. These are some of the things that you'll be learning and some of their applications. Thank you for watching.
In the school, we do more than just teach. We also do really important, exciting research. I myself look at the chemistry that's happening below the surface of the Earth and the rest of the universe. Professor Ann Jones does a different kind of chemical research. She's interested in catalysis and figuring out how nature does chemical reactions. How can they help us build our own chemical reactions, for instance, for solving the energy crisis? How do we make more fuels? How do we make interesting chemicals out of boring ones and so on? Actually, one of the chemicals she makes is simply hydrogen. Hydrogen is a really important molecule, a really important element for us. And so Professor Jones is going to tell us about hydrogen.
Hello, my name is Professor Ann Jones, and I am delighted to be part of today's opportunity to welcome the next class of chemistry and biochemistry majors to the School of Molecular Sciences. For those who are registered this semester for Chemistry 117, I'm going to meet you in a few days because I'm your instructor. For today, I have the pleasure of introducing you to hydrogen. Now, you may think you know everything there is to know about hydrogen. It is, after all, the most abundant element in the universe, number 1 on the periodic table. There's nothing going on, right? Simple element. Well, it turns out that hydrogen was produced and identified as an element in the 18th century, around 1760, by a British chemist named Henry Cavendish. Shortly thereafter, the French also identified hydrogen. And hydrogen was initially produced by pouring acid over metals. When you pour acid over a metal, it produces hydrogen gas. And it didn't take long before both Cavendish and his French counterpart Lavoisier determined that what was produced in that gas was actually an element that they couldn't break into any smaller parts. And they called it, or Lavoisier called it, in Greek, hydro for water, and genos, gen or genesis, so origin of water. Because hydrogen, upon reaction with oxygen, also in the air, generates water. So I have before you today a hydrogen balloon, and there's plenty of hydrogen in the air, in the room that we're in, but yet it's not raining. It's not making any water. Why is that? We know, for example, that hydrogen is the fuel used to power the space shuttle, right? You set it off, and the rocket blasts off into space. But yet, in this room, the hydrogen is not doing anything. It turns out hydrogen is actually not very reactive, which is why, one of the main reasons why it's one of the most, well, it is the most abundant element in our universe. If it were reactive, there'd be a lot less of it because it would react. And so why do we think of hydrogen as dangerous then? Well, for this balloon, I will show you. So it turns out hydrogen is actually not very reactive, and this is something we're going to talk about in the Chemistry 117 class, because it's a stable molecule. The bond is quite strong, the electrons are quite stable. And this is one of the main themes of the Chem 117 class. We're going to spend a lot of time thinking about what makes a molecule reactive and what makes molecules do the reactions we want them to do. For today, we're going to have a bit of fun. I became a chemist because I enjoy seeing chemical transformations. I enjoy seeing color changes. I enjoy hearing booms. I enjoy the hands-on aspect of seeing that I have changed the material world. And with hydrogen, we see that in spades. It's very easy to see that something happens when you give just a bit of energy. And that is what happens when hydrogen actually reacts. So although on its own, hydrogen is extremely stable, if you give it just a little bit of reason to react, just a bit of energy, you can get quite a reaction. And I have one extra large one. Please note that I did put my safety glasses on to do this. You do not wish to singe your eyebrows. You do not wish to lose your sight. But playing with hydrogen is quite fun. Thank you.
Yeah, so energy is important, right? Hydrogen connects to energy, and how energy goes in and out of chemical reactions is also really important. You may have heard the terms exothermic and endothermic, connecting to energy going in and energy coming out. Gary Kabarak's now going to show you some more chemical reactions. Again, look very carefully to make sure you can see the chemical reaction. And this one has something to do with energy.
Welcome, folks. I'm going to take this off, but I thought I'd start off with it to emphasize the proper attire for what your lifestyle will be like. I don't know if you heard that or not. Need to take this off. So I'm going to do a quick demo for you today, but first let me introduce myself. My name is Gary Kabarak. I am unique from most of the faculty here in that I actually did my undergraduate work here. Got my degree BS in chemistry many, many years ago, probably right about the time of the last pandemic in 1918. So I'm going to do a demo today that you've probably all seen. And I think there's even some television commercials that have this on, and actually much more impressive than this. But I'm going to give you a little chemistry to go along with it. So what we're going to talk about is catalysis, right? You know what a catalyst is. In general terms, it's something that aids or spurs something on. In chemistry, it is a substance that will increase the rate of a chemical reaction. And it's very important to say this. It's a chemical substance, but it is regenerated typically when the reaction is complete, meaning it's never actually consumed in the net reaction. I'll show you this on the board in a second. So what do we have here? Hydrogen peroxide. Now this is a higher percentage than what you have at the grocery store, which is I think 3%. This is 30%. Weapons grade hydrogen peroxide is anywhere greater than 85%. Yes, you can make bombs out of this, and you'll see why in a second. It's also been used for rocket fuel, I think dating all the way back to World War II. And you'll again see the action and understand why that's true. If it were a larger, higher percentage, this thing can be pretty powerful. Okay, so let me also bring up a little bit about thermodynamics. In thermodynamics, you're going to do a lot, but you'll also come up with some functions that tell you whether a reaction is spontaneous, right? You've heard that word before, which means it's thermodynamically favorable. Well, here's the decomposition of hydrogen peroxide, okay? Take 2 molecules of hydrogen peroxide, you get 2 of water and 1 of oxygen, plus a lot of heat. It's a very exothermic reaction, all right? If I were to, you're up here looking at this, you can see some bubbles forming, all right? So again, thermodynamics states that we can't stop this. It's naturally gonna go in that direction. But you'll also learn in thermodynamics and kinetics, Doesn't matter if a reaction's favorable or thermodynamically favorable. It says nothing about the rate of the reaction. So this thing is actually occurring right now, but really, really slowly. And so what we're going to do is add a catalyst to speed it up. So let me give you some more chemistry. The chemistry is this. A catalyst speeds up a chemical reaction by providing an alternative mechanism. And typically, you take a one-step reaction and break it down into 2 or 3. Now, you'd think, well, that would slow it down. Instead of 1 step, you got 2 or 3. But you're wrong. So let me write it up here, and you'll see. So the catalyst in this case is potassium iodide, and specifically the iodide ion. So we have 1 molecule of hydrogen peroxide plus the iodide ion. And the first step of this is this forms 1 molecule of water plus the hypoiodate ion. All right. The second step is we take the second hydrogen peroxide, right, and we react that with the hypoiodate ion. That generates another water plus oxygen plus regenerating the iodide. So here's your iodide back. Start off with iodide. So in that reaction, no consumption of iodide. Then again, you say, well, the single-step decomposition reaction broken down into 2, that's going to slow it down. You're so wrong. So here we go. We'll do it. We add typically food dye to give you a little color to this so you can see it. And then we add soap, which is necessary to take that oxygen and water gas and make a foam. Okay, so we're going to do that. All right, I think that's enough. All right. So decomposition of hydrogen peroxide, 30%. Now this will probably start off slow because the hydrogen peroxide is a little cool. I just took it from the refrigerator. Here's my potassium iodide, and step back. We'll do a shot. There we go. Ho! Catalysis.
So in chemistry, we're concerned with the periodic table. Lots of different elements, right? All these elements, right? How do we figure them all out? Well, elements have different properties, and some of the different properties are kind of cool. Did any of you see Breaking Bad, right? In the very first episode, Walter White did the thing with the colors, and the colors come from different elements. Will Comer is going to do the same thing, only he's going to do it better.
Okay, so welcome to ASU. I'm Dr. William Comer. I'm very happy to have all of you. You're going to enjoy being here at ASU, and just can't wait to see some of you, or no, all of you, walking around and everything, right? So today, what we're going to do first is we're going to go ahead and look at ethanol, and we're going to look at just exactly how flammable ethanol is. So we have our nice torch sitting here, getting ready to set some stuff on fire, hopefully not. We have our ethanol, and then we've also decided to go ahead and dissolve a few different metal salts, okay? And so we're gonna look at the different colors and properties that you'll observe when you introduce different metal salts. So let's get started, and thank goodness y'all are all somewhere safe, and hopefully I don't set this room on fire. All right, so let's go ahead and get started. All right. So we have our pure ethanol, or 95% ethanol. Simple, normal flame. This is going to be our potassium chloride, dissolved in 95% ethanol. It's supposed to be a little purplish. All right, we got strontium chloride here. Let's see what color we get from here. I like this one a lot. All right, this one is sodium chloride. This is a solid orange. That's all right. We got copper chloride. It's a solid blue hue to that. And this one is my favorite. Hopefully it works. Let's go. This one is the copper sulfate. Nice little green to it. So let's do a mixture of sorts, shall we? Let's see. Let's go. Choose some of this one. And let's go a little festive. All right, so that's all I got. Remember, safety first. Cut that flame out, and when y'all get to campus, please make sure to remember to bring your masks, okay?
So chemical reactions are all about making and breaking the bonds between atoms and molecules. But there are also forces between molecules themselves. And they're really important in controlling states of matter, liquid, solid, what something looks like, what it feels like, what its properties are. And so Clem again is going to come at the end. Last but not least, he's the most exciting one. Tells a little bit about intermolecular forces, forces between molecules in a kind of spectacular way.
Today, we're going to look at the effect of intermolecular forces on the state of matter. To do that, I have two clear liquids in these two beakers. So in this first beaker, I have some liquid nitrogen. Liquid nitrogen is boiling because the intermolecular forces, the attractive forces between the molecules, are very weak for nitrogen. Now, that's why nitrogen boils at around negative 300 degrees Fahrenheit. Those molecules are easily separated as they get warmer and have more kinetic energy. Let's compare that to water. Now, this water is near boiling. It's very hot. Water has weaker London forces than nitrogen. But why does it take more heat, a higher temperature, for water to boil compared to nitrogen? Because water boils at about positive 200 Fahrenheit, and we said the nitrogen at negative 300 Fahrenheit. So that's a 500 degree temperature difference. All right. So now we happen to have two liquids next to each other that are about 500 degrees apart. What would happen if we combined them? That would be pretty cool. Do you want to see that? I'm sure you do. Hey, I want to see it. All right, you ready? So I'll take some of the water here and I'll put it into the liquid nitrogen. Ooh, okay, that was kind of sucky. All right, maybe we need a little more water. Let's try that. So let's put all of this in here. Hey, that was a little more fun. But as we like to say, go big or go home. So we'll pause for a minute and get the next one set up. Welcome back. So what you're about to see is the combination of liquid nitrogen and boiling water. So what will happen when I pour the liquid nitrogen in here, and then I'll dump the water in, the hot water will cause the nitrogen to expand very rapidly and go from a liquid to a gas. And as it expands rapidly into a gas, that will cause the water molecules to be shredded apart into tiny little droplets, and that will form a cloud. It's not normally how clouds are formed, but it's much more fun. So, let's get to it. So there's the liquid nitrogen. And next, I add the water. 5, 4, 3, 2, 1. And there we have intermolecular forces. Thank you for watching.
Okay, so we showed you some pretty cool chemistry, right? I mean, all chemistry isn't quite as spectacular as that, but what you're going to be learning about in your career here are the factors which determine all those things that we just looked at from a molecular level. So you're going to be learning, we're going to be involved in teaching, and that's what we're here for at ASU. Well, not really, right? We actually do a lot more at the school than just learning and teaching. Remember, we talked a little bit about research, and you'll find out about that in your career here. But to make it all work, it's not just the faculty, for sure. And actually, it's not just you. The most important members of the school are you students, but we can't make the school work without a whole lot of other people too. There's lots of people here working really hard to help you be successful in your student career. People are involved in advising you, people involved in making sure that you're safe, people involved in making sure the business aspects of this place run, people involved in all aspects of pulling the whole thing together. Our whole community is really large. You are now part of it. We all want to say welcome.
Welcome. We just want to say welcome to all the new students to fall 2020 semester from academic advising here in the School of Molecular Sciences.
Welcome to 2020 fall semester ASU students.
Welcome ASU SMS students. Look forward to seeing you all and have a great semester.
And we wish you a happy, healthy, and safe semester.
And we wish you the wonderful fall semester for 2020.
We look forward to working with you. Welcome everyone. This is where you will be taking your general chemistry lab class.
Your journey learning about chemistry and biochemistry is about to start.
So the school's big, but you're part of it. Actually, you students are the most important part of it. Let's see what some of your peers have to say. Some students have already been here for a while, experienced ASU. What do they think?
Hi, I'm Nadia, and I'm a junior here at ASU majoring in chemistry.
Hi everyone, my name is Grace, and I'm a senior here at ASU majoring in biochemistry.
The polymer lab, which we did in our second semester of organic chemistry lab, and I thought it was just so interesting how the concepts we were learning in lecture could be applied to real life situations.
It would definitely have to be learning how to make aspirin. I think that was just the coolest thing ever. It was in my organic chemistry lab.
There's a lot more memorization involved in the second semester of organic chemistry. You need to memorize a lot of reactions, but also understand what each reaction does.
Physical chemistry is a very fascinating class. It really challenges you to conceptualize these really abstract concepts while also infusing physics and calculus and also chemistry.
The Noble Library I study the most in though, just because it's close to a lot of my classes.
It would have to be Armstrong Hall. The ground floor has a lot of windows and there's like a coffee shop and Einstein Bagels, so it's a good place to have study groups at, and if you just want to go by yourself to get some work done, it's a good place to go to as well.
So that's just a little insight about who we are, who you are now. I'd just like to finish by saying again, welcome. I hope you have a great semester. It's an unusual semester, right? We all know this, but we're all working hard to try and make learning as efficient and as productive as possible for you in these difficult times and as safe as we possibly can. Have a great semester. I will see you all again, and don't forget to go to the college event later today.